Hi everyone. So this is the next lecture in the series where we are understanding the advanced neural science for engineer course. So we need to understand first of all that what kind of different devices and sensors we can fabricate that can be used for this particular course, right. So we will look into the overview of wafer processing technique, but before that let me just draw some things for you. So what we call silicon, the silicon that you see here, right, I will draw here. So I ask many of my students, right, when they apply for even PhD, draw a cross section of silicon. It is very easy. This is a cross section of silicon, how we draw. Let's take a cross section and that is it. So anyways, the point is silicon is a substrate. Silicon is a semiconductor material and silicon can be used as a substrate. What is substrate? Substrate is anything over which we are going to fabricate our device is a substrate. Okay. Silicon can be substrate which is semiconductor, you can have metal substrates, you can have silicon dioxide. Now why silicon dioxide, right? What is the reason of having silicon dioxide and not only silicon? Because silicon is a semiconductor, dioxide, when you say silicon dioxide, there is a oxygen on silicon which forms SiO2. How it will form SiO2 we will go through the mechanism, but this is an silicon dioxide or oxidized silicon wafer, we call it an oxidized silicon wafer. SiO2 is an insulator, silicon is a semiconductor. Now if I directly deposit on silicon a metal, this is let us say gold, what will happen? There will be short circuit, isn't it? There will be short circuit. That is why I cannot directly deposit gold on silicon, metal on silicon, any metal on silicon. So what I will do? I will have my silicon dioxide layer on silicon over which I will deposit gold, right. Now what will happen? Now you do not have any short circuit because you are depositing gold on the insulating material, isn't it. So that is how the things are done. Now let us, so this is silicon and silicon dioxide. Just now let us focus only on silicon dioxide, but the question is from where we can have silicon, right. How can we get the silicon wafers? So there are two different techniques, one is called CZ technique or Czochralski technique, second is called float zone technique, okay, CZ FZ, float zone technique and Czochralski technique. So you start from the quartzite rock and then you have electric submerged arc furnace, you can get your metallurgical silicon, then there is a reactor, polysilicon rods to polycrystalline silicon ingot. Then while using CZ technique either you can fabricate different ingots or using FZ technique you can fabricate different ingots. This is an overview, do not worry about it, I will go in details. Okay. Point is that this is the fashion how the silicon wafers are made, okay, like this, and it goes either through CZ technique or through FZ technique, not both. And each technique has its advantage and disadvantages or limitations. Once you have this ingot, right, you do the sawing, so and then polishing. Sawing is cutting the silicon ingot into many wafers, right, and then you do the polishing and finally you have silicon wafers in a stack as you can see here. Now silicon ball and wafers, as you can see, right, we have a silicon ball and wafers. So wafers are cut from balls which are large logs of uniform silicon, right. But the question is that looking at this particular image, right, where do you think silicon balls are made and why do you think so, right. So again what you see, we have already learned in the previous class, what is this? A gowning for what? Clean room. So this is a clean room facility, isn't it. So now if you want to make these wafers out of this particular bowls, you have to use the clean room facility. So this is the and then why clean room, you already know, to avoid any contamination. So, let us go for the first technique, which is your CZ technique. In CZ technique or Czochralski technique, this is the most important method for production of single crystals, and how the process is done. So, before the process we should learn how the system looks like. So, this is one schematic of the system where you have the electrodes at the bottom, then there is a spill tray, crucible support, graphite crucible, carbon heater, heat shield, water cooled chamber, quartz crucible, silicon single crystal and seed crystal. So, what you do is you keep on heating this silicon single crystal, and depending on the seed crystal, right, the rotation happens. So, I will show it to you how exactly this works. There is a video for that, but at the beginning of the process the feed material is put into cylindrical shaped quartz or graphite crucible, which is right over here, right. Graphite crucible is this one. Okay. So, it is the quartz or graphite crucible with a few silica lining and metal resistance, so that it can be heated with a radio frequency or metal resistance. It can be heated with resistor heater, or it can be melted by resistance, or it can be melted by the radio frequency heaters. Now, after the feed material is completely molten, which you can see here, right, the seed crystal is slowly pulled up in this direction, and the direction of pulling and the direction of the rotation of this the quartz crucible, right, is totally different. Okay, it is in opposite direction. So, we will go through that. Let us not worry about it right now. The point is that when it is in the molten state, you load the seed crystal and slowly pull it off. While pulling off, rotate it. So, after the feed material is completely molten, as you can see here, a seed crystal with a diameter typically of few millimeter is dipped from the top in the frozen metal or free metal surface, not frozen, sorry, free metal surface, and a small portion of the dipped seed is melted. After that, what happens? The seed is pulled off here, withdrawn from the melt, and the melt crystallizes at the interface by forming a new crystal portion. During the growth, the diameter of the is controlled by carefully adjusting the heating power, pulling rate and the rotation of the crystal. Like I said, rotation of the crystal, if it is faster, right, pulling rate is also faster, right, then what will happen, and the heating power is lower, then you have or heating power you can change it, then you will have a smaller bowl, right, or a crystal formation, while if you have higher slow pulling rate, slow rotation rate, then you can have a bigger diameter, correct. So, that is how it is done. So, CZ technique is electronic grade used for electronic grade silicon, and the seed crystal is pulled at an optimized rate. So, like I said here, like let us understand it little bit slowly. So, the seed crystal is placed here. Once this molten region is there, and then it is pulled in this direction like this. Okay, from the hot, let us say this is hot, to the cold side, it is pulled. When it is pulled, it is also rotated like this. Okay. So, depending on the pulling rate and depending on the rotation rate, you can change the diameter of the crystal, right, or the wafer, and also the electronic grade silicon or EGS in a different short form is used in this melt, and what happens is that if you optimize this pulling rate, and the speed, your defects would be minimum. Okay, your contamination or the defects would be minimum, and you can have a constant ingot diameter. What does that mean? If I do not have optimized rate, my ingot will form like this. It is not correct, right? It form like this uniform, correct, and the tip it will be like this, correct. So, the rate of optimization, the optimization rate for pulling the crystal is very important, and so is the rotation speed. Now, you have understood about extrinsic and intrinsic semiconductors, right. So, intrinsic semiconductors are semiconductors where there is no contaminants, but when you intentionally contaminate the wafer by doping it, it becomes an extrinsic semiconductor. So, impurities both intentional and unintentional are introduced into silicon ingot, and intentional dopants are mixed into melt during the crystal growth, while the unintentional impurities originate either from the crucible or from the ambient, right. So, these are the different way of how the impurities are added. Depending on the impurity, you can say it is a N type or it is a P type, right. Boron and if it is there is a P type impurity, phosphorus N type impurity, because in boron you will create extra hole, in phosphorus there is extra electrons. So, again just let me just see the screen please. Yeah, thank you. So, the all impurities have different solubilities in the solid and the melt, and equilibrium segregation coefficient Ko is defined to be the ratio of equilibrium concentration of impurity in solid to that of the liquid. So, if I have concentration Cs by concentration Cl, so solid to liquid ratio, then I can find out the segregation coefficient Ko, and the impurities segregate to the melt, and melt becomes progressively enriched with the impurities as the crystal is being pulled, right. So, if again we can intentionally, right, dope the wafer with either P type or N type material. Now, this is from TU Delft, just let us play the video and then you will understand how the CZ technique works. So, you have seen the video, now let us see the FZ technique. Okay. You have seen the video, so let us see the FZ technique. In FZ technique, which is also called float zone technique, this is different than the CZ technique. Here based on the zone melting principle that was invented by Theurer in 1962, the FZ technique works, and in this technique what happens is that the melted zone is established between lower seed material and upper feed material. So, this is the feed material, right, this is the seed material, right, and there is a molten zone is created with RF heating, RF coil is there, and then the floating zone is moved, floating zone is slowly moved along the rod by means of relative motion of heating device in such a way that the crystal grows on the seed, right. So, so just seed is just below the melt, okay. So, the just somewhere here and simultaneously melting the feed above their floating zone. So, slowly and gradually as it goes towards the collar region, it starts forming the things. So, you can see here this is a single crystal material, this is a polysilicon ingot and the molten zone. As I told you that the lower seed material and the upper feed material, this is the feed material, this is the seed material, right, and how the molten zone is created in this particular region exactly between two by help of heating, and the seed material as well as the feed rod is supported, but no container is in contact with the growing crystal or the melt, which is held in place only by surface tension. It is very important thing to understand that nothing is supporting in this case. If you see the our CZ technique, right, there was whole support here, correct, in this thing, see, but in the FZ techniques there is no support in that particular sense. The seed material as well as feed rod material is supported only, right, by surface tension. So, the impurities in the molten region thus tend to stay in the molten region rather than be incorporated into the solidified region owing to the segregation coefficients, thus allowing a very pure single crystals to be left after the molten region has passed. So, that is the advantage of FC region, that you will not find contaminations or the impurities arising due to the technique, right. Intentional impurity is different than the one that is because of the technique. So, due to the difficulty in growing larger diameter, because you see that in this case the entire thing is depending on the molten region between the lower seed and the upper seed, you cannot have a bigger diameter wafers or ingots, right. So, the FC wafers are more expensive because the contamination will be extremely low. The FC crystals are preferably used when very low oxygen concentration is an important condition. So, CC technique, FC technique both has advantages like I said and limitations. Now, let us see the FC technique video. Okay, so you have seen the video of the FC technique as well. Now, let us understand that once your ingot, whether it is through a CZ or through FZ, right, how we can create the wafer from the single crystal ingot, right. That is very important to create a wafer, is not it. So, you start with a polysilicon and once let us come here. So, once you have this single crystal ingot, right, either through FZ or CZ, the next step is to trim the corner here, trim it, and then to have a flat grinding. Now there is a reason of when you take any silicon wafer, you will have something called one single big flat, which we call as a primary flat. Okay. And this primary flat is by creating a flat grinding here. See, there is a reason of having primary flat, and then there are secondary flats either at 45 degree or at 90 degree or at 180 degree, or there is no secondary flat. Okay. Depending on how the secondary flat is placed with primary flat, we can distinguish the wafer whether it is N type or P type, whether it is 100 or 111. So, after crystal trimming and diameter grind, there is flat grinding. So, to create a flat, and then there is a wafer slicing. Now, when we have wafer, they should be polished, right. So, first you go for edge rounding, it should be completely round, as you can see here, right, and after that you can go for lapping, followed by wafer etching, followed by polishing, right. So, this all thing will create a polished silicon wafer, polished, okay, polished silicon wafer. Now, you will say what is polished silicon wafer. So, I will show you the wafer in the next class, how the polished silicon wafer looks like versus how the non polished silicon wafer looks like. So, what happens is, depending on a single side. So, let us say this is a cross section of silicon, if both the surfaces are polished, it is called double side polished wafer, okay, double side polished wafer, double side polished, right. Is only one side is called single side polished, let us say only at the top, right. So, SSP DSP, right, single side polished, double side polished silicon wafers. If it is double side polished, it is costlier compared to single side polished wafer. The wafer diameter is larger, it is costlier, and also for creating this polishing, right, before polishing there are steps like edge rounding, lapping, wafer etching, and then polishing, and then finally there is a wafer inspection. I am sorry about the spelling, is a polishing, please read it as a polishing, it should be ISHING, polishing. And finally, you have wafer inspection, whether the wafer is correctly developed from the single crystal ingot. So, this is how the diamond coated wires are used to slice the ingot. As you can see here, it is slicing the ingot, and this will create many chips, right. And what happens that after that you use this machine for lapping, followed by the polishing, as we discussed earlier. If you want to go more and understand more about this, you can go to the microchemicals.eu, and you will have lot of interesting videos showing how the lapping mechanism works. This is one of the video from TU Delft, or how the wire direction is there, and how the wafers are sliced into the, or the ingot is sliced into the wafers. Okay. Now, the question is that we have discussed about FC technique, or we have discussed about the CZ technique, but the point is why we are discussing on silicon, right. Can we use other materials as a substrate? So, answer is yes, we can use glass as a substrate, we can use polymer as a substrate, we can use silicon as a substrate, we can use germanium as a substrate. So, there are different substrates, different materials for different substrates. But if you understand the silicon, then silicon is 90% of these devices, semiconductor devices are made up of silicon. So, single crystalline silicon and is hard and brittle materials that deforms elasticity until it reaches its yield strength. So, the point at which it starts breaking, right. So, it is a hard but brittle material. Also, the tensile strength is about 7 gigapascal, Young's modulus about 188 gigapascal, mechanical properties are uniform, good thermal conductor, and mechanical integrity up to 500 degrees centigrade. The Miller indices, if you understand the Miller indices, how the Miller indices are given. The John William Miller in 1839 helped to define the crystals or describe crystals structures, and in Miller indices are used to specify the directions and plane in the crystal, right. So, if you understand the units, Miller indices describe the crystal in terms of unit cell, how the cells are there. So, if you see something which is behind my back again on the screen, the unit cell is the smallest repetitive volume which can be repeated along the axis to form complete lattice parameter, lattice pattern, right. And how it is defined? So, it is defined as, if you see this particular cube, right, what you will have is A, B and C, and A, B, C are the edge lengths, while the alpha, beta and gamma are the interaxial angles. So, what will happen is that the A, B, C are inverted to find the HKL plane, and from HKL plane you can have either if it is negative, then it is expressed as A bar, B bar and C bar, and the brackets are used for single planes, while this particular bracket, which is curly bracket, are used for family of planes. So, what does it mean? So, suppose HKL represents a single point, in this direction you can see it is 0 0 1, right. In here is 1 0 0, in here is 0 1 0, 1 0 1, 1 1 0. You have to define the crystal planes very easily, right. So, suppose if I write H, so there are different symbols. If you write HKL represents single point, but if you HKL without comma it represents a plane, but if you write in curly brackets it represents family of planes, write in a square bracket and it represents direction, but if you write within this symbol like this, it represents a family of directions. So, depending on what kind of symbol you use, be careful, because 1 0 0 like this represents all the family 1 0 0, 1 bar 0 0, 0 1 0, 0 1 bar 0 0, 0 0 1, 0 0 1 bar. So, all the family of the 1 0 0 can be used, right. These are crystallographic planes. We will take in detail this in the TA class. I do not want to invest too much time on this, but rather that I like to invest time on understanding what is silicon wafer processing and what is one single chip, right. So, when you see the final wafer, it will come out like this, and single die is nothing but a small piece of chip on which all your transistors are fabricated, whether it is CMOS or if it is PMOS, NMOS, right. Even for the FinFETs, everything is fabricated on silicon wafer. So, silicon integrated circuits are a larger circular sheets of silicon wafers. They are fabricated on using silicon wafers, as I told you, right. And the location of an indicator circuit on a wafer is called a die site, right, which is DI, die site, and a flat on the wafer is used as a reference plane to form the grid from die placement. The number of wafers starts per week indicates the manufacturing capability. How many wafers we have started in a week? 100, 200, 400, 1000. How many fresh wafers are introduced into fabrication sequence shows the number of wafers tests. Wafers are processed in groups, not individually in the fab lab, and typically it takes several weeks for a lot to process the entire processing line. Now, there are several diameter of silicon wafer, and now we have reached way bigger than what is shown here, but depending on the diameter of the wafer, the thickness of the wafer changes. You need to understand not too much into depth, but to understand that how the diameter and wafer thickness are related. So, you can see the wafer which is 25 millimeter diameter would have thickness somewhere around this, while 51 millimeter, 76, 100 millimeter, 150, 200, 300 millimeter, 450 millimeter will have diameter which is increasing in size. So, the 450 nanometer diameter, I am sorry, the thickness increases correspondingly, not the so with diameter increase the thickness increases, right. And we have much more bigger wafers now compared to what is given in the table. Now, we talk about this DSP and SSP, as I told you earlier, right. Either you have single side polished wafer or you have double side polished wafer, and the way to polish the wafers is using the polishing mechanism. Either it is mechanical polishing or it is just a mechanical polishing. So, this process is used for smoothing of the wafer surface. We know that the smoothing is such that the wafer surface is almost few nanometers in the roughness, right. So, it is really smooth, and then there is abrasive polishing, chemical etching, there is edge countering. So, edge roughness and edge boundary or geometry is understood, rounded or blunt shape or bullet shape or beveled shape, beveled shape, I am sorry, beveled shape, different kind of shapes you can have when you have the bowels, I am sorry, bowls, not bowels, it is two different confusing words, right. So, it is bowls. So, different shapes you can find out in the ingot on the bowls. the figure side, that is A, B, C, D, you can see here, right. What does this show? A, B, C, D, E. The A shows the crown or apex, B shows the front side bevel or rounded region, and you have C which is transition area between polished side and the edge, right. You can see here this C, and then you have D which is a back side bevel or rounded region, and finally you have E which is transition area between the back side and the edge. So, this is how the things are defined, right, for single side and double side polished. Now, once you have wafer, even it is a new wafer, there is a formation of thin silicon dioxide. Okay. Why? Because silicon when reacts with oxygen forms SiO2. Okay. So, if the oxygen present in the air will also cause a thin layer of silicon dioxide. To avoid any kind of oxide when you start the wafer processing, it is important that you clean the wafer. There is something called RCA cleaning, RCA1 and RCA2. The first RCA1, the RCA stands for Radio Corporation of America, and there are two steps to remove the particulates, organic and metal contamination. The first step, which is RCA1, involves 27% NH4 OH in the ratio of 30% H2O to NH2O, and then is in that particular range we have 1:1:50, 1:1:5 at 75 degree for 10 minutes. You have to dip the wafer and heat it at dip it for 10 minutes, and the temperature is about 75 degrees centigrade. This RCA1 cleaning will help to remove the organic contaminants and particulates, while RCA2 cleaning, which is a mixture of 73% HCl is to 30% H2O2 is to H2O in a proportion 1:1:6. This again for 10 minutes at 75 degrees centigrade. This will remove any metal contaminations, right. And finally, there is a HF dip. HF dip is used to remove the silicon dioxide and thin layer of silicon dioxide that is grown when it is exposed to the air. So, that is 49% HF to H2O in ratio range of 1:50. So, let me play this video and then you will understand more about the how the silicon chip, from when it starts, how the fab lab works, and how we see the end. Great. So, here the next step would be the application of silicon dioxide in IC industries, right. So, where exactly the silicon dioxide is used, okay, and what is the thickness of silicon dioxide that you require. So, there are two techniques to grow silicon dioxide, one is called wet oxidation and second is called dry oxidation. In wet oxidation you use the vapor or water vapor of course, and in dry oxidation you only use the dry oxygen. So, depending on the type of the oxidation, the thickness of the oxide on the silicon wafer will change. Now, if you go for 1 micron to 1 nanometer, 1 nanometer is a native oxide, like I said earlier, that when you keep the wafer in the air, when it is exposed to air, the oxygen, there will be thin layer of oxide that grows on the wafer, which is the native oxide. But if you use it for gate, it falls somewhere in 10 nanometer. If you use a masking oxide, it can be 0.1 micrometer. For field oxides, it is 1 micrometer. For masking oxide is 0.1 micrometer, from field oxide it is 1 micrometer. What is field oxide and what is masking oxide, right? So, let us understand at least the masking oxide. The field oxide is, so this silicon wafer, and let us say that we need to create the pit in silicon wafer like this, okay. So, you and for etching silicon you can use TMAH, tetramethyl ammonium hydroxide, or potassium hydroxide. This is at 80 degrees centigrade and this is at 25 degrees centigrade, either or, okay, either or. So, if you dip the silicon wafer in one of the solution, it will start etching, but if you dip the silicon wafer, then what will happen, the thickness will start reducing, correct. So, what you use is a masking oxide. That means you create, you deposit or you grow the silicon dioxide onto silicon wafer, okay, perform photolithography, and when you perform photolithography you just save the silicon dioxide from the back side, and in front you protect silicon dioxide in this region, and here you can see that this area of the wafer is exposed, right, this area of the wafer is exposed. Now this wafer, if I dip it in either TMAH or KOH, what will happen? This will start etching silicon dioxide, which is here silicon. Silicon dioxide will not get affected. SiO2 is a masking oxide. The rate of etching of silicon dioxide in this solvent, which is solvent for etching silicon, is extremely slow compared to the silicon. So, when you dip this wafer into a TMAH solution or solution with KOH, then this will form the pit, as you can see here. No, not like this, okay. Of course, there is a silicon dioxide here and there is silicon dioxide here. Now, once you know the rate of etching, you can stop etching, you can take out the wafer and rinse it with H2O2, right. After that, what we wanted? We wanted wafer to look like this, correct, silicon wafer. So, you after this silicon is etched, you dip this wafer, entire wafer into BHF. BHF stands for buffer hydrofluoric acid. Now, BHF etches silicon dioxide, it will not affect silicon. So, if you dip this wafer, this one wafer with W, entire wafer, okay, entire wafer, you dip it in BHF, then what will happen? The oxide will get etched. When oxide gets etched, you have the silicon wafer here. So, the point that I am making here is that the oxide, silicon dioxide, which is around 0.1 micrometer, can be used as a masking oxide, okay. And for the gate oxide, you have to use 10 nanometer, somewhere around that thickness of the oxide. So, you can see here in this particular image what is called as, if I have silicon dioxide on silicon wafer, right, then if I do HF dip, right, only silicon dioxide gets affected, silicon will be protected, right, in a different way you want to show it. So, very good etching selectivity between Si and SiO2 using HF. So, HF will not affect the silicon, right. So, that is the point, and then in TMAH or KOH, the silicon dioxide etching rate is very low compared to silicon, and thus silicon dioxide can work as a masking oxide. Another work is that silicon dioxide, when you dope with different contaminants like boron or phosphorus or gallium or arsenide, right, what will happen is that the dopant cannot pass through silicon dioxide, okay. So, what kind of dopant you want to introduce, what kind of contaminants you want to introduce, depending on that and diffusing the time of the diffusion, right, the thickness of oxide would change. For example, if you want to diffuse boron at 1200 degree centigrade for about, let us say 10 hours, then you have to see what is the thickness that you require. Here is 10 hours, 1200 degree centigrade, and somewhere it is matching here, right. So, you should have somewhere of 0.2 microns. 0.2 micrometer thickness silicon dioxide will work. But if I want to do the same thing for phosphorus at 1200 degree centigrade for 10 hours, so this becomes the phosphorus. So, you should have somewhere around 2 microns thick silicon dioxide, got it. So, that is how the masking oxide, so SiO2 mask for boron and phosphorus. This is a chart through which we will know what should be the thickness of the silicon dioxide, right. Can also be used to mask against ion implantation. So, ion implantation is another technique to dope the contaminants into the silicon. When say contaminants, is not really it is in a way for N type it is a P type contaminant or a dopant you will say, okay. Impurities, not really contaminants, we will say impurities. So, this is deliberately intentionally added to the silicon wafer. For N type silicon wafer we add P type impurity, for P type silicon wafer we have N type impurity, sometimes within the well we can have N type impurity. So, depending on what kind of transistors you are fabricating. Now, like I said, there are two types of oxidation technique, one is wet oxidation technique and another one is a dry oxidation technique. So, let us see how wet oxidation technique works versus how the dry oxidation technique works, okay. So, in this case you can see dry oxidation and wet oxidation. The dry oxidation is silicon which is solid, when it reacts with oxygen which is in gas form, it forms silicon dioxide, and for the wet oxidation it is SiO2 plus H2O gives SiO2 plus H2O gives SiO2 plus H2, balancing equation 2H2, balance equation here 2H2O, right. So, this is how the equation is balanced. For the what is the advantage and disadvantage, both typically works in the same temperature range 900 to 1200 degrees centigrade, right, but wet oxidation is faster than dry oxidation. Wet oxidation quality is poor compared to dry oxidation. Dry oxidation generally is used for gate oxides, thin layer or very thin layer gate oxides, and if you want you can add the nitrogen to form oxynitrides, while the wet oxide is generally thicker, faster to grow, but it suffers due to diffusion of the hydrogen gas. You can see here, right, hydrogen gas will come out, right, which causes the paths for the electron that can follow, or the because what will happen, because of the diffusion that happens, the hydrogen when it comes out through the diffusion technique from the silicon dioxide, it forms this hollow regions or some paths through which the electron can follow, and that is difficulty. So, that means that wet oxidation cannot be used for gate layer oxides, right. Room temperature silicon in air creates a native oxide which is about 1 to 9 nanometer, is very poor insulator, but can impede surface surface processing of silicon, and that is why when you have a new wafer you have to do a HF dip, from RCA1, RCA2 and HF dip. This is how the total oxide thickness is determined, right, and then there are several techniques to grow the silicon dioxide. I think this is enough for this particular lecture. You have understood silicon, you understood silicon dioxide, you understood dry oxidation, wet oxidation, and the oxide can be used for masking oxide, field oxide as a native oxide, gate oxide, and let us understand the techniques to grow this silicon dioxide onto silicon wafer in the next class, which is the thermal oxidation methods. I will go in detail in the next class. So, till then if you have any question you can ask through the NPTEL portal, right, and we will take it from there. We will learn thermal oxidation first, and then we will also learn the thermal evaporation, E-beam evaporation, by which you can deposit different materials, metal, insulator, semiconductors. Sputtering is part of it because we call as a physical vapor deposition techniques. Then once you understand that, we will go for photolithography, which is the heart of fabrication technology. Once you understand how these techniques are used, then we will start attending important problems in the area of neural science and in the area of brain, right, to address some important problems and the corresponding device for the same. So, I will see you in the next class. Till then, you take care, just learn these things, right. Some of the topics that I say, some of the words that I use, just Google it and see what are the differences, okay. And I will see you in the next class. Till then, cheers.